This video is sponsored by Brilliant. I want to push myself to do hard things, although the first hard thing is walking and carrying all of these textbooks here in one hand. I've locked myself in a bus out in the Australian bush with no phone, no internet, just a bunch of textbooks about fractals, and I can't leave until I master this topic. I know a little bit about fractals already, but not a lot. I know that they are these self-similar shapes that can appear a lot in nature. I know one example would be something like a fern plant where it's got like that main branching shape which is similar to each of the little leaves, and they have this similar repeating pattern at multiple levels. Actually, I've just seen that there's this fern-like shape here, although it's a plastic one, but this is what I mean, that this main shape here looks similar to each of these little individual ones. I know of some of the famous fractals you can draw, and I do know that not all fractals are self-similar, that it doesn't have to be the same pattern repeating at multiple scales, but that there is some detail at multiple scales. So let me give you a bus tour. We've got the door, the window and the driver's seat. Here I have my stuff, my camera and a bunch of textbooks I got out from the library before coming here. A little outside deck, although I'm not allowed to go out there. May I introduce you to the food that I have for this challenge? These tins of beans right here are it. These are my rations. I have a producer who is going to test my knowledge by slipping some envelopes with questions under the door, and if I get them correct, then I get rewards that help to make studying easier, and if I get 5 correct, I get to leave. We've got stuff about fractal dimensions, fractals in geology and geophysics. This one sounds interesting, fractal space-time and microphysics, the beauty of fractals, what shape is a snowflake, magical numbers in nature, fractals and multifractals in ecology and aquatic science. But the book I'm most looking forward to read is this one over here. This is Mandelbrot's book on fractals, called The Fractal Geometry of Nature. And since Mandelbrot was the guy who came up with fractals pretty much, or first communicated them, I think this one is going to have a lot of really special knowledge in it. Mandelbrot opens with, "Why is geometry often described as cold and dry? One reason lies in its inability to describe the shape of a cloud, a mountain, a coastline, or a tree. Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line." Mandelbrot says that there is a Latin saying that to name is to know, and he names these complex natural patterns fractals. One of the first examples of a fractal that Mandelbrot gives is the coastline paradox. The coastline is surprisingly hard to measure the length of because there is detail at every level, zooming all the way down to the atomic sizes. If you used a small ruler and measured around every rock, you would get a much larger answer than if you used, say, a 1,000-kilometer sized ruler to measure it. There are a couple of different ways of measuring the dimension of something. The first is topological dimension, which is an integer value reflecting the number of coordinates needed to specify a point within the space. It's intuitive and straightforward, with lines being one-dimensional and planes two-dimensional, and so forth. Another way is the Hausdorff fractal dimension, which extends beyond integers to include fractional values and is a cornerstone of fractals. It quantifies the degree to which a fractal fills space. This page shows some data of measuring the length of coastlines in different places. You can see that the coast of Britain is especially steep in this regard compared to attempts to measure the South African coast. They stabilized off a bit more. And a circle, which isn't fractal, it's just an ordinary shape, that stabilizes pretty quickly. And so it doesn't matter if you use a smaller ruler to measure the circle, you're going to, for the most part, get the same result. Perhaps this means that the coast of Britain is especially fractally, and Mandelbrot says down here that he had the idea of using the slope of these lines as an estimate of 1 minus d, where d is the fractal dimension. I've just seen a wild deer. I don't know, I've never seen one before in Australia. I might follow it and go have a look. Oh, there it is. I actually love staring out of a bus window, just sitting there, watching the world go by usually, but this is a stationary view, which is a bit different. I think some of my best thoughts that I've had have just been, you know, sitting on a bus or a car, just like looking out the window. I could do that for ages. I am starting to really stress actually because I don't know when the first question is going to arrive, and it could be any minute, so I'm kind of on edge, and that's not helping me to absorb the information. I've been reading for a couple of hours now, and I feel like I don't really know if I've learned anything new. The anxiety that I'm feeling now is kind of hitting at why I was motivated to do this challenge, which is like this fear of mine that I'm becoming not very good at doing hard things, that even my focus it feels like it's not as good as it used to be. I want to feel like I do have a good grasp on a lot of topics so that I can talk about them. My worry is that the question will come and that I'll get it wrong, and then I'll get all of them wrong, and then this will be embarrassing and I'll feel like I haven't learned anything, and I'll have to really go back to the drawing board. I want this challenge to be a way for me to prove to myself that I can still do things like this, that I can still learn new ideas. Here's one interesting passage I've read so far. The fractal dimension is a measure of the roughness of the features. Earth's natural features are created by tectonic processes and modified by erosion. Erosion seems to be scale invariant, so its influence is the same on the small features as it is on the very large. That's why a river network is an example of a fractal. When the same force of nature acts at multiple scales, we see similar features appearing. I think the lack of yummy food is actually affecting me more than I thought it would. When I conceived of this idea of like just eating beans, I was like, yeah, sounds good, sounds fine, sounds easy. I don't know, I don't want to. I saw Beau Miles eat a whole bunch of beans that looked like he ate them cold, so I feel like I can. It's grim, but it's not too bad. Kind of tastes normal. Okay, this is actually good. Maybe I could actually do this. I think maybe a problem that I have is that often to like start work or, you know, to start doing something hard, I often wait until conditions are perfect, right? So like I've eaten something good, it's like not too hot, not too cold, I'm feeling not too tired. Basically waiting and doing all these things in my day to make it feel perfect and the right conditions before I even start. And I can feel myself wanting to do that. It's like hard to study right now. It's like hard to read, but I actually want to exercise that muscle of discomfort, of pushing through and doing something hard even when the conditions aren't perfect for me. One thing I'd like to be able to learn is how to calculate fractional dimensions. As you might know, I have a passion for dimensions, thinking about the fourth dimension, things like this, and so the idea of dimensions in some sense being these in-between spaces between 2 and 3 dimensions, between 1 and 2, 3 and 4, maybe being able to calculate and understand what it means to be a fractional dimension. What does it mean to be 2.5D? And lucky for me, I've encountered a pretty simple formula in the book to measure the fractal dimension. The thing you are measuring, such as the perimeter or area, should be a constant given by multiplying the total number of fragments by the size of each one raised to its dimension. Let's take the area of a square, for example. It's in one piece, so n is equal to 1. The length of each side is 1, but we're talking about area, which is 2-dimensional, so d is equal to 2. So the formula will be 1 times 1 to the power of 2, which is equal to 1. Imagine breaking the square up into 4 fragments. Now n is equal to 4, and the length of each of the smaller squares is 1/2. Still, the dimension is 2, So we have 4 times a half to the power of 2, which is still equal to 1. This approach can be used to work out the fractal dimension of any shape. The first question has arrived. Ooh, okay, so this is about the coastline paradox, which I did read about. Alright, let me just have a minute. Which of the following statements is true regarding measuring the length of a coastline with a ruler? Is the dimension less than 1? I don't think so. An increase if we use a lot. I don't know. I actually don't know. Let's just see. The length of a coastline tends to converge to a single value, D, in a dimension greater than 1. But no, I feel like none of these are right. Okay, I'm panicking. I don't know. I've got to pick something. I've got to pick something. I'm taking too long. I'm just going to say A, okay, because I'm taking too long here. The answer is in here. The answer is D. In a dimension greater than 1, the length of a coastline remains almost constant as we decrease the size of the ruler. Okay, I've gone back to my book and found a paragraph that explains why I got that one wrong, but I think it does clear it up. It's this paragraph here about the fractional dimensions. It says that the approximate measure in the dimension D is independent of epsilon. Now, epsilon is the size of the ruler, and the measure in this case is the length of the coastline. So if we can measure the length of the coastline in the dimension D, which is the fractional dimension of the coastline, then it's independent of the size of the ruler we use. And the fractional dimension of the coastline happens to be about 1.26, so it is greater than 1. So if we look at our question, there is indeed a dimension greater than 1. In fact, it is at about 1.26, where the length of the coastline remains almost constant as we decrease the size of the ruler. A previous reader of this book even underlined this section here, which is what was stuck in my brain when answering this question. It is that if you approximate the coastline's length in a dimension smaller than its fractional dimension, then the length will go to infinity as the size of your ruler goes to 0. That is the normal case where we're essentially using an ordinary one-dimensional ruler, also known as a straight line, to measure the length of the coastline. We can't measure it with these one-dimensional rulers though. We need our rulers to be 1.26 dimensional. Okay, so that was kind of a lot, but I appreciate the question because I skimmed over some of this stuff and I guess I didn't really get it until now. I had just thought, yeah, small ruler, your length will go to infinity. Not always the case, depends on the dimension of the ruler. What's unfortunate about getting this first question wrong is that I haven't received any of the rewards, but the first one that I would receive is fire, and I do have some candles over there, and so that would allow me to get a little bit of light for studying tonight. Yeah, that'll kind of ruin my plans of doing more study tonight if I'm not able to unlock this. I found a good example of using that formula to calculate the fractal dimension of something that is not quite a line. Take a line of length 1, divide it into 3 parts of length 1/3. Just keep the 2 end segments and throw the rest out, so n is equal to 2. Now repeat that process. The remaining fragments are split into 3 parts of length 1/9. Keep the 2 ends of each, and you now have 4 fragments. Now, can we find a dimension in which the total measure of the line remains constant? We'll just set these 2 equations equal to each other and solve for D. Doing so results in this formula with logarithms in it. Putting in our numbers, we find that the dimension in which the measure remains constant is D is equal to log 2 over log 3, which is 0.6309. It's less than a line, but more than a point. This example is known as a Cantor set. In some porous materials, the distribution of voids can resemble the process of removing segments, similar to the Cantor set. Coral reefs grow through a process of branching, which can also create complex, self-similar structures at different scales, much like the iterative removal of segments. The fractal-like growth patterns of coral allow for efficient use of space and resources, with the intricate branching increasing surface area for sunlight absorption and nutrient exchange. This is exciting. Okay, another chance, a chance to save myself. Alright, so, okay, here's the question. Which of the following statements is true regarding the two definitions of dimension, topological dimension and Hausdorff dimension? So I did read about this earlier. I know that it can be a fraction, and that's where we get this idea of fractional dimensions. Okay, so is it A, that the topological dimension may be an integer or a fraction? No, because I think only the Hausdorff one can be a fraction. B, a fractal is a set that satisfies the Hausdorff dimension being bigger than the topological dimension. That does ring a bell. I think I did read that. C, the Hausdorff dimension cannot be equal to the topological dimension. Yeah, that seems consistent. Wait. The Hausdorff dimension cannot be equal. I'm going to go with B. The answer is in this one. Okay. The answer is B. So that's one. Yay. Okay. We're 1/5 there. We've got a reward. Okay. This is great news because it is getting a little bit dark soon. Still light now, but we might have some candles tonight. I've got to confess that I am a little bit afraid of any kind of fire, even lighting candles, which is why I'm being so awkward in these clips and standing over the sink. These pictures go hard, and the Gaussian hills that never were would make for a cool album title, but they also demonstrate that to make video games and models look the most realistic, fractals should be used in the simulations. I had my dinner and did some more reading, and then late at night on the first day, the third question arrived. Let's see what's in this one. Here we go. Mandelbrot coined the term fractal because of the following meaning. A, fractional dimensions. B, it is a factual way to organize nature. C, it was inspired by branching patterns created during fracking. And D, it is based on the Latin fractus, breaking into irregular fragments. I do remember reading something like this in the Mandelbrot book, and Mandelbrot is the guy who actually came up with the name fractal, so I believe what he has to say on the matter. So I'll go with D. It is based on the Latin fractus, meaning breaking into irregular fragments. I remember that irregular fragments part because before I was reading this Mandelbrot book, I did think it was A. I thought it was fractional dimension, but no, I'm going to take Mandelbrot's word on this one, so I'll go with D. Here is our answer. Okay, that's good. That's a boost for the morale tonight. I do get to tick off something on the board though, and that's going to be this one here, which is writing, just to be able to take notes, and I actually get to keep the notes that I take as a bit of a cheat sheet. It's been hard to study without this because it feels like just reading for reading's sake, but I really find it useful to be able to write down and organize my thoughts. And on that, I think I'm going to go to bed pretty soon, just because candlelight's not quite as easy as I think the sunlight's gonna be. So good night. I got up to take a video of the deer who was back again, but then the morning got absolutely derailed when I spotted this spider. I had to prop the side door open a bit to get it out, but from this moment on I was living in fear and sleeping with one eye open. Everywhere I sit, I am now on the lookout for more spiders. I do have one friend on board. Their name is B, and that stands for Benoit B. Mandelbrot. I might try to explain some concepts to them later on, but for now I'm going to leave them up here on this curtain rail to keep a watchful eye over me. Fun fact, algebra derives from the Arabic word meaning the reunion of broken parts, so fractal and algebra come from opposite meanings. These are the note-taking implements that I am rewarded with by getting that last question right. I just saw what I think was 2 foxes going past the window, so it was pretty cool. It's nearly 4 o'clock and I've been studying all day with no questions coming through. So I've received a heads up that the next question will be based on 2 chapters from a particular book. And it's pretty good that the next question is from here, because I've been reading this one. I found that it has really clicked with me in a way that the Mandelbrot book didn't. I had this tiny tinge of disappointment that I won't walk away from this challenge feeling like I know fractals. Instead, I'll be feeling like there's so much more to learn. Fractals are a big topic that impact so many different fields, right? I've been reading some of these books and I'm just amazed by the amount of different places that fractals show up that I had no idea about. Like in this book here, there was a chapter about fractals like in mining and gold deposits. And I was reading that chapter and realized that just trying to understand that chapter could be an entire challenge video of its own, and that there's definitely entire careers to be made out of studying fractals and even just some of the use cases in which they appear. This does kind of make me feel like I'm cramming. I'm sort of bit of an anxiety that there is a time pressure, that there are questions arriving any minute. And so I'm a little worried that I will forget a lot of this content, but without doing this, I wouldn't have made much progress through these books at all. So I'm hoping that at least something sticks, and that at least some new ideas start to form, and then I can build on them later if I want to. It's very quiet out here, very still. It's a little bit boring in some sense, but in another way, there's no place I'd rather be. Here it is. I don't want to open it. I feel like I'm not ready. Like I want to feel more prepared. I don't know. This is the state of my cheat sheet of notes when the question arrived. So it wasn't full. I was like still planning to make some more notes down here. Okay. You measure the length of the coastline of 3 different islands, Island X, Y, and Z, using 4 different rulers with lengths 10 centimeter, 1 meter, 100 meters, and 1 kilometer. Each ruler gives a different result and you plot them on a graph. Which statement is false? This is kind of like that graph that I showed you yesterday actually, where one of the gradients was flat and that was for a circle, which isn't fractal at all. For a non-fractal shape, it like at least levels off or is flat. D, Island Z has a smoother coastline than Island Y. Wait, no, yeah. Okay, that's the one that's false. I'm gonna say D. Yeah, it can't be smoother than Y. It just can't. It can't be smoother than Y. Answer D. Yes. Okay. This is great. I'll also be able to use real lights from now on, the overhead lights, which is going to be great for my eyes. This is a really small joy, but I need it. This actually smells great and looks really good. No, it actually looks really good today. I like it. If I had some cheese and rice to go with this, it wouldn't be a grim meal at all. It would actually be one of my favorite meals. The sooner I can escape the bus and go outside, the better. I love being in here and learning, and I love learning about fractals, but you know, it hurts to be out here, but then locked in a bus. It's like I'm in nature, but so close yet so far. To be honest, I think if I was able to go outside and do walks and do things and be more in control of my life, I think I would actually study better. I don't think that all of these hours that I've spent in here have been productive hours. Many of them have been, I think, non-productive. I don't think what I'm doing is the best or far from the only way to learn. I was just taking a minute to stare at the ceiling, but I heard another envelope get dropped off. I'm excited, but I'm also nervous. I've still got my same cheat sheet with me from earlier. Okay, we can do this. This should be good. All right. I really love opening these. You are taking a random walk when you notice an odd-looking tree. Examining one of its leaves, you determine it can be constructed the following way. In each iteration ABC, all side lengths are equal. What is the fractal dimension? I've got a couple of formulas that help me calculate the fractal dimension. What I need to know is how many fragments it's been broken up into and like the size of each of those fragments. Yeah, that would have to make sense, that it's been broken into 1, 2, 3. What I needed to do was just look at the first order change. We started with 4 lines of length 1, then squares are added into each fragment. We now have 20 lines of length 1/3, since 3 fit along the original side. Put those numbers into the logarithm formula to find that d is log 5 over log 3. But I muddled up the bottom and got log 1/3 instead of log 3. This caused me to panic and enter a tailspin for 20 minutes, trying various other techniques which would have worked had I not made more basic errors. Oh my god. Eventually I picked log 5 over log 3 because I could tell it was close to my answer in form, and I knew it was in the right ballpark even if I couldn't explain the discrepancy. Yes. Yes. Okay, it says C. I've been solving this for like half an hour. Ticking off technology. And here are my rewards. My phone and my laptop. Okay, I get to use these and I get to connect to the internet for the next part. I received a message that the next question would be about the Mandelbrot set, so I did some Googling and even watched a few number file videos about it. I found that understanding the Mandelbrot set starts with understanding the behavior of numbers when you square them. Some numbers, when you square them, blow up and go to infinity, but not all numbers. 1 stays the same no matter how many times you square it. And numbers less than 1 will actually decrease if you square them. The Mandelbrot set explores this line between stable and unstable points, where unstable points are those ones that blow up to infinity. In particular, the Mandelbrot set is defined by this iterative formula that starts at 0. You square it and then add a complex number onto it to get the starting point for the next iteration. If C, the complex number that you're adding each time, causes the value to blow up to infinity, then C is not in the Mandelbrot set. If instead C causes the value to go to some stable fixed point or to 0, for example, then C is in the Mandelbrot set. To see what I mean, let's take a look at a few numbers and see if they are in the Mandelbrot set. Let's take 1. Starting with 0 squared plus 1, that's 1. Square 1 and add 1 and you get 2. Square that and add 1 and you get 5. Square that and add 1 and you get 26. And it will keep going to infinity. So 1 is not in the Mandelbrot set. Let's try I, which is the square root of minus 1. 0 plus I is I. Then I squared plus I is equal to minus 1 plus I. Then square that and add I, and it actually works out to be just minus I. Square that and add I, and again you'll get minus 1 plus I, and you'll continue toggling between these values. So I is in the Mandelbrot set. In this shape here, anywhere that is black is a point in the Mandelbrot set, and the coloured points are ones that go off to infinity, but they're coloured based on how quickly they go off to infinity. It's a very interesting mathematical pattern. When you zoom in on various parts, you will find the shape repeats. It is fractal because there is repeating detail and self-similar structures at every scale. It has a fractal dimension of about 1.3. It's more than a line, but not enough to be a filled-in shape. It's amazing the complexity that comes out of this thing because fundamentally it's defined by quite a simple rule. This artwork is made by just marking points that, when squared and then added to themselves in an iterative way, remain stable. So I'm feeling a little bit down actually because I realized that I got the previous question right, but not because I actually got it right, more that I got it close enough and essentially guessed the right answer. And I've had time to go and think and realize how it was done and where I actually made a mistake. I used a 3 instead of a third anyway, and then I used something else wrong the second time. So I did all this working and I got close enough and I got the answer, so I'm going to allow it. And you know, guessing is allowed in this game I've designed in the sense that it's multi-choice for a reason. If you don't know, you should have a 1 in 4 chance of getting it right. So I got it right and I'm moving onwards, but I feel like I really had 2 or more brain farts in the process of doing that working out. And so for that reason, I'm going to call it quits for today, go to bed, and hope that I'm a little bit fresher and more onto it tomorrow. I've just got out of bed this morning to find one more question, and this could be the last one. Oh, there's no answer in this one. Okay. Visit brilliant.org. Navigate to complex numbers / the Mandelbrot set. Complete the final question correctly to escape the bus. This question is sponsored by Brilliant. Brilliant is an interactive way to learn math, data science, and computer science. What I like about Brilliant is that I get to test my knowledge by answering questions, which helps me feel like I actually understand what I'm reading. Their courses are also fun and allow you to work at your own pace. Their course on complex numbers covers the Mandelbrot set and the related Julia sets by first covering the properties of complex numbers, which are important to understanding these particular fractals. You can get started on Brilliant for free for 30 days, and the first 200 people get 20% off an annual plan by visiting brilliant.org/Tibees. If a point C is in the main cardioid, then the process of squaring and adding eventually results in a single fixed point z, such that z squared plus c is equal to z. If x is a real number in the Mandelbrot set, what's the maximum value of x? Oh my god, this is quite hard. 1/2 is the largest of these numbers, so that seemed like a good place to start. Initially, I tried to just see what happened if I squared these numbers then added them to themselves, to see if that would be stable or not. But after several iterations of this Mandelbrot function, I would have a number that wouldn't really tell me definitively if it would keep getting bigger or converge to some fixed value. And so it wasn't clear without doing a lot more iterations what would be the long-term behavior of these things. So I ended up using the hint on Brilliant, which gave me this equation that z squared plus x is equal to z. Initially, I didn't see how this would help, but I realized this is to do with the fixed point. What I mean is for numbers that are going into this Mandelbrot function, either they will blow up to infinity or they might oscillate around a stable point, a fixed point. So some value that it converges to, no matter how many times you put it into this function. In this equation, that fixed point is represented by z. It's saying that if you've done enough iterations to reach this final fixed point, then you square it and add your number on, you should end up still at that fixed point. So I just need to find which one of these 4 fractions is the largest one that satisfies this equation. That seems kind of tricky, and starting with putting 0.5 in just to see what happens, we get this quadratic, which actually doesn't have any real solutions. You could try to complete the square or use the quadratic formula on this, but the only z that you'd find which satisfied it would have an imaginary component. So let's try the next biggest one, which is a third. Putting a third in leads to the same problem, that there is no real solution for z in this quadratic equation. The next one to try is 1/4, and rearranging it to have z squared minus z plus 1/4 being equal to 0, you could complete the square quite easily actually, and find a z value of 1/2. That's pretty cool, and we can see that it works. If you're already at the point 1/2 or 0.5 and you square that, it becomes 1/4 or 0.25, which is how much you're adding back on. So you're going to end up with what you started with, 0.5. And no matter how many more iterations of the Mandelbrot function you do from this point, you will stay there. The largest real number in the Mandelbrot set is also the point on the real axis that is furthest to the right. So this red dot here in the picture above the question. That's what I'm saying should be 1/4, and eyeballing it with the axes that are given here looks about right too. So I'm gonna go with that. Oh, I'm nervous because I really want to go. I wanted to make a graceful and profound exit, like they do on The Bachelor when they slowly step out of the car. Instead, this is the exit I made. Running in fear from what is objectively a tiny threat. Oh my god. I have a big problem on the... This is the final boss. If it jumps on me, I'm dead. I am dead. I'm just going. I'm going. I'm going. Oh my god. Oh my god, craving something like this for a while. How do I eat it? That's really good. I don't think I became an expert on fractals. I think maybe I learned enough to be able to sustain a conversation about them, but I feel far from being an expert. In fact, it was the simple things that nearly defeated me on this challenge, logarithms and the quadratic formula. So if anything, I could just spend 3 days out here relearning the basics of maths, but I'm glad I did it. It was fun to do. I look forward to doing something like this again. See you next time, and thank you to my Patreon supporters for making these videos possible. Shout out to today's Patreon cats of the day, Duchess and Princess.